All right. Parallelization technique is same as in prims, right? I'm not going to redo the parallelization because it's exactly the same. There's no difference at all. All right. So the parallelization is exactly the same. If you recall, right, what is the speed up we had achieved for this? The speed up we said was, this was the expression, right? This was it. Okay, so speed up was this. So if I just take P to the numerator, ideally I like my speed up to be P if I'm putting in P processors, right? So what is this? This is not exactly P, but it's P upon theta 1 plus theta P log P by N. Okay, and I said that, I can get speed up proportional to the number of processes I put in as long as the number of processes I put in is N by log N. If I set P equal to N by log N, then I'll get good efficiency, right? Okay, anyways, the crux is that I didn't have exactly P, but I had a pretty good one, right? This denominator is some factor, but it doesn't hurt too much, right? Okay. Now, as we had discussed right in the beginning of the course, right? Real world graphs are sparse. So let's relook at this algorithm. Well, prims or SSSP. Let's just look at SSSP, right? In the context of sparse graphs. So what will happen? Can you take out the sequential time? What is the sequential time of execution? So what does it mean for a graph to be sparse? On average, number of neighbors is constant, right? Since every processor is dealing with a large number of vertices, we can assume that the total number of neighbors for all the vertices put together is some constant times the number of vertices. Okay. Let's come back to this algorithm and let's analyze this. So how long is this algorithm going to take? What is the sequential runtime? So let's ignore this part, right? I don't care about this part. This is just order n, right? Let's come over here. So first we are looking at the sequential algorithm. So first of all, there are n minus 1 iterations, right? So this is already order n, right? You're already doing order n iterations. What are you doing inside each iteration? Finding the min, right? So how long does that take? Well, if you do sequential, it takes order n. And then what do? Some vertex is going to get added, right? And then you have to go and update all the neighbors of that, right? If we are talking about a dense graph, then this is order n, right? I'm going to have to update all the neighbors. Is that okay? So that's why we had got, theta n square. I mean, I can replace all of these with theta. That's okay, right? So that's why I had got a theta n square in my sequential time when I had analyzed it for Prim's algorithm, right? Okay, but now the point is that if we have a sparse graph, what's going to happen? Well, this is going to be some constant. Yeah. Every node will only have a constant number of neighbors, right? So the time that I spend in updating all my neighbors and doing the relaxation operation is only going to be constant. Some C, right? Let's say C. Is that fine? C maybe the max degree of a node or the average degree, right? Something of that sort. Okay. Now, can I afford to do a linear search to find the minimum? Earlier, I was doing a linear search and I didn't care about using an efficient data structure. Why? Because I was anyways going to have to spend theta n time in going through all the neighbors and updating them, right? And doing the relax operation, right? So therefore, I didn't care about finding the min, right, in a more efficient manner. But now that it's a sparse graph, the relaxation for a given node does not take too long. Yeah, it's almost done in constant time. So now I can't afford to do this min operation by a linear search anymore, right? So this doesn't work anymore. So I have to change this. And how do I change this? Well, I'm going to use a priority queue, some priority queue. So what will this time become if I use a priority queue? This will become login. Yes, is that fine? And what will happen over here? This operation is also not constant operation, right? If it's a priority queue. Earlier it was constant because I could store it in an array and I just had to replace that value. But now if I'm maintaining a priority queue, every time I update a value, I have to readjust it in the priority queue, right? It's already there in the priority queue. So I have to readjust it. Is that fine? Each of these will also take theta log n. Is that clear? So let's assume that the average number of neighbors is C, right? So then what's the sequential time? So there are n iterations, and in each iteration, the total time is about C log n, C plus 1 log n, yeah, theta C log n. So the sequential time now becomes, I don't need to write C, it's a theta asymptotic notation, but let me just write it, okay? Yeah, generally in sparse graphs, the number of neighbors is constant, but I'm just writing C so that, in case it's not constant, you can keep track. So this is going to be C times n log n. That's the sequential time. All right. Now, how do you implement this in parallel if you're maintaining a priority queue? So last time we were not maintaining a priority queue. So what I'm going to do is I'm going to make each processor responsible for n by p vertices. Yeah, standard stuff, right? Just like we did last time. Okay, so essentially what this means is that I partition V into P disjoint sets. Let's call them V1, V2 to VP. Right, so this is pretty much like your 1D distribution. For shared memory, I generally don't call it a 1D distribution. Now what we'll do is each processor is going to maintain a priority queue. So let's talk about processor I, right? So each processor I, maintains priority queue. I'll call it PQ of I over its vertices. Okay, let me just step back. Okay, I just need to be slightly careful. I just told you that find u such that du is equal to min of this, right? So what happens over here is that if I'm going to maintain a priority queue instead of arrays, I need to tell you how to set up the priority queue, right? So what is my priority queue going to look like? So initially I'm going to set my priority queue equal to V. All the vertices are in the priority queue. Okay. And then in every iteration, so this min is actually, in terms of priority queues, it's called an extract min operation, right? So that's standard stuff in algorithms terminology. Extract min from priority queue. So how do we find the minimum? We basically perform an extract min on the priority queue, right? So that returns me the min. But what does extract mean? Basically, that means that, so this is the important part I wanted to just emphasize on, that U is no longer in the priority queue, right? I have removed U from the priority queue. That's because if you recall, the vertex which has the shortest distance, tentative shortest distance, in every iteration, if you remember this graph, this example that we were taking, in every iteration, the vertex which has the shortest path, I basically include it in my tree. I don't need to update the distance value of that anymore, right? Who do I maintain this priority queue over? I only need to maintain this priority queue over these vertices, the vertices which are not yet covered, right? Is that clear? I don't need to maintain the priority queue over the vertices for which I have already found the shortest distance, right? These vertices which I have included in my set T, for these the D is frozen, right? The shortest distance is frozen. They are already in the tree. which means that I don't need to maintain the priority queue over them anymore. My priority queue only needs to resolve amongst the vertices which are not yet included. Okay. Coming back, right? So what is the implication of using a priority queue instead of an array for finding the min? Initially, my priority queue contains all the vertices. So in this step, when I find the minimum shortest distance in the priority queue, I basically pull that vertex out of the priority queue because now I know the shortest path to that. All right, let's come back. In sequential, it's kind of obvious, right? But we need to be now slightly careful when we are dealing with the same thing in parallel. So each processor I maintains priority queue over its vertices, right? So how are we going to initialize? Initialize the priority queue with B of I, right? I include all the vertices initially, right? Again, remember, each processor only has a view of its own vertices and their adjacency list, right? So I will only initialize with my vertices, right? The priority queue. Okay. So what I'm going to do is I'm going to maintain D as before for its own vertices. Okay. In addition, I'm going to maintain something called a D bar. And it'll just become clear in a few minutes why I need to maintain two copies, right? One is D, one is D bar. D bar is the value in the priority queue, right? PQ of I. So think of it as the following, right? That while the algorithm is running, D bar is what's there in the priority queue. And D is the shortest path, the actual shortest path, right? And when I pull out something from the priority queue, I know its distance is frozen, right? On extracting a node U from priority queue, update D of U equal to D bar of U, right? So the point is that in the priority queue, the value keeps changing. Once I pull it out, I associate a value D of U with it. Okay? Just bookkeeping, don't worry too much about it. They're essentially the same thing. Here is the key point, right? That when I pull a node out, extracted node is settled locally. What does this mean? So what is settled, right? Settled basically means when U is pulled out from the priority queue, right? Then U is no longer in the priority queue. It is basically frozen. In other words, settled is just another word for frozen. Settled means that shortest distance has been determined. Shortest distance from source has been determined. All right, that's all we mean by settled. And that's the time I add it to the tree T, which means that I already know the shortest distance, right? So settled means it's in the tree. I've already put it in the tree and the shortest distance is frozen. But what's going to happen in the parallel case? So each node is going to extract the min element from its priority queue. Okay, and it's going to treat it as settled. But actually, that may not be true because if I have 10 processes, I cannot settle 10 vertices at a time, right? By the correctness of the Dijkstra's algorithm, right? The way I need to do it is I need to just look at the min. I can only argue that the one which has the minimum distance is settled. I cannot argue that any of the other ones just because the processor has a local guy who's minimum. Only the global min guy I know will be settled, right? So I say that the extracted node is settled locally. And what may happen is that it may get activated again later on. All right. So that's the key here. Every node will pick up their min element, and either I can do a synchronization across all the processors, right, and find out that who's the global min. And then, everybody will just update based on the global min. But that's not efficient. Okay, so I want to be doing more work in parallel. So each processor should be doing some work, right? As we saw in the previous case, right, that will not lead to good speed up. Sorry, I wanted to cover something which I didn't cover in full. I wanted to take out the parallel time and the speed up. Okay, so I'll just come back to this. Okay, so what we are going to see over here is that speed up is going to be bad. When you're using priority queues and when you're dealing with sparse graphs, then the speed up is really bad. Okay, so we'll just come back to this and show this. That means obviously that's not a good parallelization technique. And now each processor has extracted its node locally, and then they do a global, let's say globally they find out who's the min of them all. Then our speed up is going to be the same as the speed up that we'll just come back to. Okay, so the speed up is going to be bad again, and we don't want a bad speed up, right? So what we're going to try to do over here is we are going to try to do this work in parallel. So each node is going to extract its min, and everybody is going to operate on their min vertex and do the necessary operations, right? We'll see what these operations are. Okay. So this is the important part, that the extracted node on a processor is locally settled and it may get activated later on. All right, now what will we do? We'll basically look at all neighbors, right? In order to examine all neighbors, I need to send messages now, right? So if it is a distributed memory paradigm, then I have to send messages to owners of all neighbors of the extracted min vertex, because they may not be local. In case of shared memory, I don't have to do any send, but in the case of distributed memory, I have to actually do a send. So what do I send to a neighbor? So let's say I have extracted U, right? And then I look at all neighbors of U, right? So I look at all the neighbors of U. What am I going to do with all the neighbors of U? I'm going to send, let's say V. Let me rewrite this properly. For all neighbors V of U, what are we going to send? We are going to send, who are we going to send to? We are going to send to the owner of V. And what is the value we are going to send? We are going to send that U is the vertex from which I'm trying to reach you. And the distance I have via U for U is D of U plus WUV. All right. Yeah, I can just say U comma V, right? This is the edge, source destination, and this is the tentative distance, right? So what is the receiver going to do? Receiver will examine message, right? The message it receives is U comma V, and it also receives this distance, right? The receiver is the owner of V, right? This is the owner of V. So what is he going to do? He's basically going to check if the current distance he has for V, right? If that is greater than DU plus WUV, if then update. Clear? Any questions till this stage? So that's basically the strategy, right? This is the strategy we are going to do. So we'll write the pseudocode for this. Let me just step back for a second here, right? Parallelization technique that we used for prims, that's what we were discussing earlier. If we use the same parallelization technique that we use for prims, even for the case of sparse graphs where we are using priority queues, what is the parallel time going to be? So again, there are n iterations. I can't do anything about these n iterations, right? So I still have these n iterations. And the min operation, I can use priority queues. Each processor will be responsible for n by p of the vertices, right? So this is going to be n times log of n by p. If I'm dealing with a sparse graph, the blue ones are all the changes I was making for the sparse graph. If I'm dealing with a sparse graph, I'm not going to go and update this value for all the vertices in v minus t, right? Because there aren't going to be so many vertices. I don't have to look at all the vertices. All I need to do is, instead of looking at this, I just need to look at only neighbors of u, the element that has just been extracted, right? That's the Dijkstra's. Is that okay? I hope this is clear. Look, in the dense case, I went ahead and updated the d value for all the vertices that I owned, right? For all the vertices, essentially. This is the sequential algorithm. But in case of sparse graphs, I shouldn't be doing that, right? I shouldn't be going and updating dv for all the other vertices. That's an overkill because there are order n vertices, but the number of neighbors of u is only constant. And those are the only ones that are going to change because I have just extracted u and frozen its shortest distance. So I just need to look at the neighbors of u and relax them. Is that clear? So in the sparse case, I'm not going to do this for all v in v minus t. For the sparse case, we were capturing all the changes in blue, right? So there will be an additional change here. I will not be looking at all the vertices in v minus t. I'll just be looking at only neighbors of u and only relaxing those. That's how we get this sequential time of C and log n. Then let's come back to parallel, right? So we had already started discussing the parallelization strategy. Let's not talk about that. Let's just talk about parallelizing this simple Dijkstra's algorithm, right? That's all. So what's going to happen in the case of parallel? How do I find the min? That we said, okay, log n by p, right? Because each processor can find the min of their elements. Then you may have to combine them, which is going to be another log p, right? Just to combine the min across all of them and determine the overall min. And then how many elements do I update? I have to update some constant number of elements. C elements I have to update. So maybe I can divide that amongst the processors, right? So C by P. But how long is each update going to take? Again, it's going to take log of. Is that okay? What is the time I'm saving? Well, I'm maintaining different priority queues. So updating those priority queues doesn't take log n time, but takes log n by p time. Yeah. Why is this bad speed up? What is the speed up I'm going to get? It's almost going to be constant. I'm not going to get anywhere near p factor speed up. What is the problem? Let's just divide these expressions. So parallel time, just get rid of everything else also. Let's just keep the first term, right? So what is the speed up? The speed up is going to be theta sequential time Cn log n by, which is the largest term here? Let me just take a log of n by p, right? Let me take C as constant and remove C also for now. N log n by p. There's an n outside, right? N log n by p. And what is this? N cancels out. What is log n by p? Log n by p is just log n minus log p, right? Again, if n is large, that's just log n, right? N dominates. So this is like theta 1. What is the problem? Look, we were expecting that when we put p processors, our time reduces by factor p, right? But the problem here is that with priority queues, right? Earlier it was taking log n time to search for an element. Now I've divided the priority queue among p processors, so it's taking log n by p time. But log n by p and log n are asymptotically the same, right? When n is much larger than p. Okay, is that point clear? So I'm not gaining anything in the priority queue. Okay, so that's why this is really bad. I'm not getting any speed up. So sparse graphs are always a problem to deal with. So in this approach, in this new parallelization strategy, right? Let me just call this parallelization strategy, new parallelization strategy, right? I'm trying to overcome the bottleneck caused by this bad speed up, right? So what I'm going to try to do, and that's precisely what we're trying to do over here. Each processor is going to extract a min node from its own priority queue. And we are going to do a relaxation for all these vertices. Okay. So we are not doing a relaxation for one vertex, we are doing a relaxation for p vertices together. Now, theoretically, this may not lead to any improvement in the worst case, but the point is that in practice, this really, really, really does well. Okay, this is what brings you parallelism. And what you can argue is that with this, you can complete your operation in number of iterations, which is equal to the diameter of the graph. Okay, so obviously, as I said, right, in the worst case, you can always take the diameter to be order n, which means that you'll not get any significant speed up, right? But in most graphs, that's not the case, right? Diameters are not so huge.